Have you ever wondered how machine learning works in predicting prices of second-hand cars? In this episode, we will go through the process of analyzing, coding, and predicting car prices using available data. We're going to perform a method of supervised learning using k-nearest neighbor on the data that's available from CarDekho. CarDekho is India's #1 auto portal, and they're gracious enough to share the data on Kaggle, and we'll be processing over 8,000 transactions of cars sold between 1994 to 2020. This would include data including the year of the model, the number of kilometers that it has driven, the fuel, the transmission, the engine type, so on, and of course price, so that we can predict price based on this specific feature. So a brief background on k-nearest neighbor. This essentially works by predicting the price based on the nearest neighbor in terms of similar features of the price. So in this case, if we want to know the price of this house in the large star, we can look at the prices of other houses near the area and do a weighted calculation so that we'll be able to predict roughly how much this house would cost. So similar approach will be used to predict car prices. But before we can do that, we need to perform several steps beforehand. Of course, we need to analyze data, we need to clean up the data, do some feature engineering, normalize the data. We might need to reduce or select types of data that we need to include in our analysis. We will then perform k-nearest neighbor and look for the best hyperparameter that will perform the best on the given set of data. We will also look into principal component analysis, which is a dimensionality reduction technique, so that we can simplify the entire operation. So let's get started with this Python notebook that includes step-by-step instructions on how you can perform data analysis and machine learning on this available data. So the Python notebook already includes instruction, what you can perform and where you can download the available data. So it has a link already to the available data set in Kaggle, and we are going to perform data loading, pre-processing, initial modeling using KNN. We'll then perform principal component analysis and some conclusion. Essentially, at the end of this activity, you'll be able to realize that we are able to achieve up to 87% accuracy in terms of prediction, but only after performing some transformation on the data to get a more accurate result. So let's go through the code one by one. So this is the import statement. We then load our data on the CSV file of CarDekho and take a quick look on the data. So in here, we can see that we have access to the name of the car, the year it was sold, the selling price, kilometer driven. Also, there are several categorical data as well as numerical data. So first step towards exploratory data analysis is for us to clean up the data. This would include removing the duplicates. So in here, we found that there's about 1,200 duplicate records. We want to remove that. And we look at the columns. We want to simplify some of the column names. We also remove rows that have null values. And we can see that from 8,000 records, we have now reduced to about 6,700 records. We'll do a basic analysis of what the data looks like. So in here, we can see that most of the cars are manual and automatic, and there's a mix of between petrol and diesel engines, and there's a first hand, second. So this gives you an idea what is the distribution of the data that we are processing. At the same time, we realize that these data are actually categorical, and we have to convert categorical data into its numeric representation. There are different ways that we can convert. One is to convert the values into an ordinal value. For example, in this owner, because it's first, second, third, we can replace all first owners with 1, second owner with 2, third with 3, so on and so forth. However, there are also cases like where it doesn't make sense to make them ordinal, like individual or dealer. We can do one-hot encoding. So in the next couple set of codes, we are doing just that. We converted the transmission into ones and zeros, and we converted the owner type into 0, 1, 2, 3, 4, as well as converted fuel and the seller type into a categoric one-hot encoding. So if we now take a look at the data set, you'll see that most of the columns, actually all of the columns, are already in numerical format so that we can perform our operation. But before we do that, let's do a correlation analysis of the data set. So we'll do a heat map, which is essentially telling us how correlated one data is with the other. So in here, we can clearly see that fuel petrol is highly correlated with fuel diesel, and it's a negative, obviously, because if the engine is petrol, it's not diesel. So this is essentially the purpose of doing correlation heat map. In our case, we're looking at the selling price. So we want to analyze what data are highly correlated with the selling price. We can see that the year is highly correlated. At the same time, transmission is highly correlated. You can see engine is highly correlated. Max power is very highly correlated. So we can look at these 4 features as main features that affects the selling price. And if we go dig down a little bit further, we can also look into the distribution of data across the different features. So we can do a histogram plot to see how distributed the data are in terms of the year and the seats. This gives us some insight of how widely different the data is. At the same time, we can also notice that the values of each of these data are very far from each other. Year, for example, is in the year 1995 to year 2020, while the number of seats is only between 2.5 to less than 10. So to ensure that we get equal weights for each of the features, we would like to do a standardization of the result. That is to normalize the data between 0 to 1 so that they're all treated with equal importance. But before we do that, let's perform the k-nearest neighbor on the original scale of data. So we'll assign first our, which is the target. So we want to predict the selling price, to identify the selling price here. And we use the rest of the data as our features. And we then perform a split of the train and test data. So in this case, we are separating 2 sets of data. 20% will be allocated as test data, and then the 80% will be training data. So this will automatically allocate it. We then perform k-nearest neighbor, considering 5 neighbors, and perform the prediction. This code actually loops across different values of neighbors or different k from 1 to 10, and we will measure the performance of each of the value. So we then execute this, and then we get this plot of accuracy. So we can see that in terms of training data, our performance is slowly degrading as we use more values of k. In terms of the test data, we get the maximum performance at around k equals to 4 or k around equals to 3. However, we can also notice that the performance is below 50%. No? It's around 0.4697 in terms of performance. So that's the best performance we can get if we do not normalize the data. So let's go ahead and normalize the data. This code normalizes the data, and we perform the same step again. We will loop through from 1 to 10 and see how this model performs. And immediately we can see that the performance is so much better as we are already hitting above 80% accuracy on the test data. So we're able to see that if we normalize our dataset, we immediately get a significant gain in terms of performance. Now, one of the issues of running this test is it actually takes a long time to perform. In this case, it took us more than a minute and a half to do all these tests. So we will look into how we can improve the runtime performance of this model by choosing only selected features that of high importance to the selling price. And we've identified earlier from the correlation map that transmission, max power, and year are the most important features that affects the price. So we will perform the same operation but only use 3 datasets instead of the entire 16 datasets. We then perform the train test split and do the graph again. And we can see that we're able to complete the entire operation in 14 seconds. That's about 1/10 of the original time that we had earlier. So while it runs faster, we're also getting a much better performance. And we can see that with reduced features, we're able to reach up to 87% accuracy in predicting the price. As a side note, we'll also look into principal component analysis. As mentioned earlier, principal component analysis is a way to reduce the dimension of your data by prioritizing the features that has the maximum impact to predicting the selling price. There are already existing PCA library that is available in scikit-learn, and you can use that. And we can perform then a variance analysis, right? So this EV ratio essentially shows us how many features or how many principal components would represent the behavior of your data. So, for example, if we are targeting an 80% accuracy, then you can look at this line and we can say that with around 5 or 6 components, you can get 80% of accuracy in terms of representing your entire dataset, which may be sufficient already. So if we look at 80% accuracy, then we can choose, for example, 6 components as our feature set. So we perform PCA again, and this time we will specify 6 principal components and do an analysis. So in this analysis, we can look into the different loadings of the different features. So these are the different components. So from the original 16 features, we will then reduce that into 6. And if we want to know which factor is heavily influenced by center component, we can look at this heat map. So in this heat map, we can see that PC1 is heavily influenced by fuel petrol and fuel diesel, as well as the engine, right? So all these 3 features are being highly regarded by principal component 1. And then if we look at principal component 2, it would refer to the seller dealer, seller individual, as well as nothing else, right? So using this heat map, we're now able to see which component represents which value from the original set of features. So now we will perform KNN again on the reduced component, and we can see that we're able to reduce the time also. No, it's a bit longer. It's a bit longer than the 3 components because this time we're using 6 components, but still so much faster than using all the feature sets. And we are also able to achieve an accuracy of about 81.2% on the PCA set of data. So some of the lessons we've learned from this activity is that standardization and normalization of the features are important. Correlation matrix is also useful to identify which features are of high importance to the prediction, and that if you have smaller features, naturally you will be able to improve the runtime performance of your algorithm, and PCA may be a good representation for dimensionality reduction. If you enjoy watching this, click like and subscribe, and thank you for watching another episode of Artificially Intelligent.